Okay, here we go. This is John Gonder for, well, in this case, the CAS 76 Wireshark class, but this is going to be up under bonus lectures, so it's applicable to any class where we're analyzing the operation of a system and specifically using Wireshark and understanding it in terms of where the problem lies. We know that we have 7 layers with our OSI model that define the various jobs that get done. And a very basic way of troubleshooting is simply to work our way up the OSI model and verify operation or a problem at one or more of those layers. There's 3 basic areas where things are happening when we have 2 systems that are communicating in some way or trying to communicate in some way. And one is the application itself we're using on a client machine or on a server machine, which has layer 7, layer 6, and layer 5 aspects to it. We'll go into more in more detail. And that is as separate from, as we'll see when we analyze this particular problem, the operating system itself, which operates at layer 4, layer 3, and layer 2 in this communication system. And then there's the network itself, the physical connection, whatever method it is, between one end and the other, and whatever devices might be in the middle, and their operation overall from one end, a source, to the other end, a destination, and back and forth. For things that are happening at the application layers, our application, Outlook, Office, whatever, and layer 6, the encryption or decryption of that information that's being utilized in or out, and the session layer, managing the session between an application and a server or between 2 applications, for instance, login, name and password. We may or may not be able to really clarify what's going on or not going on within those 3 layers at the application. We may be able to define there's a problem or there's not a problem. We may or may not know more clearly at which of these layers that problem occurs. For the operating system, layers 2, 3, and 4, the transport layer that manages our pipeline through which our data session passes, the network, the path from one place to another across the net, the data link layer, which manages the creation of proper packaging frames to go on whatever physical layer comprises the network we're using. Those 3 layers, again, we should be able to tell a fair amount about what's going good or what's going badly with regard to the operating system. With regard to the network, again, we'll see in a very clear way what is happening or not happening with the network, and we'll be able to decide where we need to place our energy, where we need to place our thoughts to resolve this problem, or at least pass the right information on to the people whose job it is to resolve them. So in this particular case study, this was a trace file taken of trying to have a connection with the GroupWise POP email server on the Las Positas College campus, and that email was not working. So this is a relatively small trace file, and it is on the net for you. I will not say inside this video because the location of that may differ. If you want to try to follow along, I will email the classes that I'm working with about where this trace file is so that they can follow along directly. But otherwise, everything that you need to know about the information in this trace file should be pretty clear from this presentation. So I'm opening up this trace file in the current version of Wireshark, which is version 403, and I'm using a profile of mine that makes use of, on the right hand side here, the packet diagram, which allows us to very easily see where things are and at which layer they're occurring inside packets. And we can see in this trace file that it is really just 28 packets long. That's all it took. Obviously, this was a longer trace file when it was captured because there was more happening on the net. I filtered for the packets only between my client station and that POP server. So for instance, what we don't see here is if there was a domain name server request from the client station for the IP address of the POP server. Well, let's take a look first. Of course, we know in terms of TCP that in order to create a pipeline from A to B, we have to have what? The three-way handshake. Synchronization request, an acknowledgement to that, and a synchronization request from the opposite side, and then an acknowledgement from the first side. And in that exchange, then they tell each other some of the options that they are willing and able to do, and then come to an agreement about how that pipeline is supposed to operate. Let's take a look at that a little bit more closely here. So this is .31, my client station. We're capturing on that client station. And .14 here is on the same subnet, actually. Well, actually a different subnet. .208.31 versus .2.14 is the actual POP server. And via protocol with a length of 78 bytes and an ID of that packet, so we can match up from the local IP port given to this particular conversation, 50099, to the standard POP port for email, 110. Here's a synchronization request. Let's look more closely inside that. Well, I've got a destination MAC address, which is my first hop toward that. I've got a source MAC, which is my own network interface card. And inside that Ethernet frame is being carried IP version 4. Well, IP is version 4, total length. Are there some flags? Time to live, so it doesn't go forever on the net. And what we're carrying inside this IP packet is TCP. And the source IP address of this box is .31, and the destination ultimately where we're going is this 172.28.2.14. Well, scrolling farther down at the TCP layer, the source port that's assigned to this conversation on this client, 50099, destination port, we're looking for somebody who's listening on port 110. And typically that will be our POP email server. Sequence number, acknowledgement number, nothing yet because we're not sending any data. So we're not keeping track of the packets that go down there to see whether they were received properly. What we do have here in this SYN packet is options. And let's go over here and see. So this is how the client would like to operate. I say, my client says, I have a maximum segment size of 1460 bytes. And I'm not using window scaling, timestamps, selective acknowledgments for packets is permitted, and that's it. Well, okay, that's fine. And then we get from the other side, .14.31 in packet 2, a synchronization request, an acknowledgement of the first SYN. Yep, yeah, I see your SYN. That's cool. And you know, further, I am ready. I have the CPU time, I have the space and time to have a conversation with you as well, so I'll synchronize with you. Now this time column here is set to be currently the seconds since the first captured packet. What we really want is seconds since the previously displayed packet. So if we're starting out at 0 at number 1, this is an important piece of information we're going to look at in just a second here. Well, let's look inside that packet. And of course, the same thing. It's an Ethernet packet from that end to this end. It's carrying IP version 4 from .14 to .31. And inside is TCP from port 10, destination 50099. Now we've got an acknowledgement number 1 because we're starting to send stuff back and forth. And here's the options that the server wants. It says, well, he has a maximum segment size of 1460 as well. And no window scaling, and SAC is permitted. So agreement on both ends is made. So if we're having a problem with communication, what does this tell us? It's not because they can't agree on how to open a TCP pipeline from one side to the other. And the other important piece of information here, remember, we're talking about trying to figure out what's going on at these layers. Well, we're looking at basically 2 packets that went back and forth across the network, created by the operating system on this side across the network, and then up the network into the operating system at the other side to generate our SYNAC. Well, what does Wireshark tell us about that? Well, the process of sending this packet, wherever that was, having that box think about it, whatever amount of time it took to realize it's okay and send a SYN request back, and then to come back across the network was what? About 5 milliseconds, which is pretty quick. Well, we saw that the IP addresses indicate they're pretty close and in the same enterprise. It isn't like we went around the world. So we expect to see that fairly slow. And then in 125 microseconds, this local box sent out that acknowledgement. So this represents the time it took for the operating system to get that information up from the network interface card through layer 2, layer 3, and to the transport layer, layer 4, and say, okay, cool, now we're good to go. We have a pipeline from A to B. Now the next thing that happened is 5 milliseconds later, we got another packet from .14, and this was actually POP protocol, and it was coming from the application itself. So up till now, we've been dealing with layer 4. 3, 2, and 1. Now that that pipeline has been created, layer 7, 6, and 5 can communicate across the net. And what do we see? Let's take a look. Packet 4, Ethernet frame going across the net, destination and source carrying IP version 4, time to live, source address .14, destination address .31, coming from the group-wise server to our local email client, destination port 50099. And there's some payload in here. What is the payload? The payload says, well, we're post office protocol, and I'm just telling you that I see that we are connected, and I'm okay. We are ready. The POP server is ready. Well, we'll see about that. Well, what happens next? Well, now our local client has seen that the folks on the other end are ready, and so our local client now, in a very short period of time, right, 000089, now says, okay, sending an acknowledgement. Notice this is TCP, so what layer is this? Layer 4. This is the operating system saying, yes, we received your message and I have given it to the application. Here's where sometimes we'll see a difference between it's a very quick acknowledgement, but maybe not so quick to get the application to do whatever should be next. We have to keep in mind where these messages are coming from in the layers. Layer 4, layer 4, layer 4, layer 7, layer 4, and now we have a message from .31 to .14 at layer 7 saying, okay, cool, you're ready, so I'm going to give you my username, Jay Gonder. And that was 113 milliseconds later. So it took a few milliseconds for this application to get its act together. Or maybe this was actually, once that happened, I had to type in my username. Sometimes we'll see a considerable delay here on one end when there has to be user input. And that doesn't mean something's wrong. It just means it took me, a minute to type in my username. Next, 4 milliseconds later, we get what? From 14 to 31, TCP layer, layer 4 at the operating system sends an acknowledgement. And our sequence number, we're keeping track of how many bytes are set. We'll talk more about this in other situations because we're centering here on and analyzing what's happening here, not necessarily TCP sequencing. But got an acknowledgement from layer 4, says, yeah, I got that, and I handed it up to layer 7. And then what happens? Between this packet 7 and packet 8, 82 seconds go by. That's a very long time in net years. And now the operating system, which previously had said fairly quickly, yeah, I'm ready. As soon as we go to do something, I give it my username. It's kind of choking on that. We don't know really what's happening at the other end at that layer 5, 6, and 7. We know layer 4 was really quick at that end, but it's 83 seconds before we get, or 82.38 seconds before we get an, oh, okay, got your username. And then I acknowledge my client very quickly at layer 4, TCP, acknowledges receipt of that packet. And then again, pretty quickly now, the local application makes a POP protocol message that says, well, here's my password. Well, that's not my real password. I changed that for this presentation. I'm sending you the password at 66666. And again, from .14 to .31, in a very short period of time, the time that we previously defined as the time it takes the normal delay to get across the net and get back, about 5 milliseconds, 4.9 milliseconds, we get an acknowledgement from their operating system at layer 4. Yep, got the packet. Now it's all ready for the application to pick up and chew on. And actually now, pretty quickly, we got from that application pop message that says, oh, okay. So sometimes it's fast, sometimes it's slow. Do we necessarily know why? No. Do we know the network is consistent in its operation? The time of a message going down and coming back is consistent. The acknowledgments from layer 4 at the TCP layer, we're sending something, we get an acknowledgement, the packet is received at the other end, is happening in very similar time. It's very dependable. What we haven't seen be dependable yet is the operation of the application at the server end. See where we're going, see how much we can know just in the space of 6 or 7 packets. Well, 9 or 10. So we got an OK. Packet 12, locally, very quickly, I say, yep, got it, cool, all right. And then I say, okay, I want to give you my user identifier, which identifies my email account. Once again, the other side at layer 4, TCP, acknowledges that very quickly. And in 283 milliseconds, it's not 83 seconds, but this is what? Previously, when we had an acknowledgement and we got an OK, it was like a millisecond later. Now suddenly 283 milliseconds go by before POP identifies my user account and says, okay, a unique ID listing follows. Because that's the process. I log into my account. It says who I am, which account I'm talking about. The other end has to identify that, find that information wherever it might be stored, and then be able to give me a list of what there is, maybe new that I need, new emails to come in. Okay, unique ID listing follows. And very quickly, at my end, at layer 4, say, okay, I acknowledge receipt of that packet. And now the POP system starts to send some information that is 105 bytes. Up till now, these have been really short packets. That, hey, what you doing? What's your name? Hi, here's my name. What's your password? Here's my password. What's your UIDL? Okay, here it is. Okay. So there's not much data there. Now we're starting to see some information. Let's take a look at this packet here. Packet number 18. Well, again, what's the outside? Ethernet. Inside, we've got IP. Inside that, we got TCP, source port 110, destination port 50099. Sequence numbers and acknowledgement numbers are incrementing as we're sending, not a whole lot because it's not much data. And here's the actual payload. Well, the payload is Post Office Protocol information, Internet Message Format, that's the IMF part of that. Right here where we said it's Post Office Protocol Internet Message Format. And the payload is message text, so here's some identifiers for our message. Well, now we're starting to see stuff in Post Office Protocol language at packet 18. Packet 19 is my local one saying at layer 4, yep, I got that. And now I see that, so now I send the list command, which is to give me a list of everything that might be useful to me. And there's more to that command, but just, okay, I sent a list command. And now the other side at layer 4, the operating system, very quickly acknowledges that. Remember, 005 is our normal internet delay transmission time there and back. So that part is still working fine. And then very quickly, the operating system has passed that information to the server. Server has very quickly said, okay, got it. And I'm going to send that list right away. Yeah, good luck with that. So that message comes in, my local client at layer 4 very quickly says, yep, oh cool, there you go, I got that. And then we get 64 bytes of POP IMF when a minute later, a whole minute later, a minute. Well, this is a very long time for the client to wait for something to come in. Let's take a look at this packet and see what was in there. So, right, once again, Ethernet carrying IP version 4, source destination address, source port, destination port. Here's the payload. It's Post Office Protocol in that payload, Internet Message Format, and there's what we got. Not much. Not much. As a matter of fact, and it took so long that my client timed out and sent a reset, which says, I'm done. I am out of here. And at the POP layer, the message included there, after another 119 seconds, not even hearing from the other side, I said, look, I quit. I'm done. Well, we still haven't heard any reply from layers 5, 6, and 7 on the other end, but we do get, and I'm sending a fin and an ACK, we do eventually get an acknowledgement of that fin packet to be finished. from the other side, but from what? From layer 4 in the operating system. We still have not heard from layer 7 at the other end, but it's taken so long now that we are timing out at our end. So what do we know? What have we proved? Well, network layer, good, all the way. Layer 2, 3, 4, TCP operation, acknowledgments, sending, good, all the way. Layer 5, 6, 7, that server application, we don't know what's going on. It may very well be the case that an email system has more than one box. It may very well be the case that the information storage for mailboxes is on some other unit. Often there'll be its own little world there of IP addresses and boxes and databases and the actual box with an application on it and then a duplicate application. So can we see from here, can we see with these packets inside that little world on the other end? No, this is our only view to that world on the other end, which is this IP address and whatever responses we might get in post office protocol that are coming from somebody at layer 5, 6, and 7 on the other end. Whether or not the inability to actually retrieve and give us the information we want deals with is a problem with them being able to talk to each other, information not being able to be retrieved, the system is too busy, the application is not too busy, but the database is too busy. Those are questions to look further at that location if we can, or we just let the folks who run the email system know what that problem is. But from our standpoint, not being able to get our mail, we have proved everything that is on our end is working fine. Our application, our email application, comes and picks up those packets from layer 4, makes a response very quickly. Layer 4, 3, 2, and the network send those across to the other side very quickly. So in the space of a very few packets, by knowing how the system works, knowing how the OSI model lays out the jobs at different layers, we have very easily determined everything that we can from looking from this particular point of view, capturing packets on the client. I really love this way of being able to present a visual picture of the structure of the packet within Wireshark so that we can very easily see the relationships of each section of the packet, what is enclosed within each layer of the packet. The Ethernet system is enclosing our IP version 4, which is enclosing our transmission control protocol, which is enclosing whatever is the layer 7 application that's currently operational, is currently sending or receiving this particular packet. So we can very clearly see the operation of the network, the operating system, and the application. So that's a quick and dirty analysis of slow email. Well, so slow that our local client just gave up listening because it took too long to try to get information from this email application that worked a little bit, didn't work, worked a little bit, didn't work. And that's the way to use Wireshark, step by step.